Hello everyone, this is our project titled Analyzing Discrimination and Fairness in Binary Decision Making, a Bayesian approach making using PYMC3. This is our team members, Jay Krishna, Saujanya, myself and Hemant. This presentation will cover the theory of exploratory data analysis and how it can be used to make prediction. This presentation will also discuss the importance of exploratory data analysis. This code implements a Bayesian data model in PYMC3 for quantifying bias and discriminability in binary decision making, leveraging logistic functions and posterior sampling. It yields metrics like mean true positive rate, false positive rate, and estimates of bias and discriminability, serving as a foundation for decision making research.
In binary decision making, discriminability measures the separation between two Gaussian distributions, indicating the observer's ability to distinguish between the categories. Bias reflects a consistent preference for one category over another, manipulating within the code to stimulate and impact on the decision making. Using Seaborn, the script generates the kernel density plots for sample of discriminability and bias parameters, illustrating their probability density distribution. Labels, legends, and access information are added for the clarity. The code utilizes the Seaborn function to generate the kernel density estimation plot for distribution for TP and FP rate. It employs in T samples and B samples as input data, with the label specified for each distribution, visual comparison, and parameters uncertain. The top two lines of code create a kernel density estimation KDE plot for the 4 datasets. The labels for each distribution are discriminability, bias, TP distribution, and FP distribution.
This code generates a kernel density Seaborn estimate plot for 4 datasets using it visualizes distribution of true positive rate, discriminability, false positive rate, and bias. Labels are added for clarity before displaying the plot. This code employs NumPy's NP standard function to calculate the standard deviation of samples for discriminability and bias parameters. Theano's eval function coupled with the standard methods determines the standard deviation of TPR and FPR distributions. This standard deviation value serves as metrics for assessing uncertainty and variability in model parameters and performance measures, aiding in model comparison and estimate precision evaluation. Calculates the discriminability and bias by finding the mean of the respective samples, prints the discriminability and bias values.
The code computes the standard deviation of discriminability and bias parameters using NP standard from NumPy's. It also utilizes Theano's eval function and standard method to find the standard deviation of TPR and FPR distributions. These values gauge uncertainty in model parameters and performance metrics, aiding in model comparison and estimation precision evaluation. The code employs NumPy's NP standard function for D samples and B samples arrays, the Thea's eval function with standard method for TPR and FPR distributions to calculate standard deviations. These metrics gauge uncertainty and variability in model parameters and performance measures, aiding in model comparison and precision assessment. Void main throws exception. This line defines the main function of the code. Qcate discriminability by our distribution and distribution. This line is a comment that mentions discriminability, bias, and distribution, which are likely key aspects of the code. Bayesian estimation techniques were employed to estimate TPR and FPR distributions as well as discriminability and bias parameters. PYMC3 facilitated sampling from posterior distributions, enabling mean estimation for discriminability, bias, TPR, and FPR. Thank you.